Okay, now we'll continue from question number 11 to question number 15. And that question has been given in Calcutta University Honors Examination. So first we will define the image of a function. So let f a to b be any function and then the image of f is denoted by IMF or FA and is defined by image f. This is equals to all those fx such that x belongs to a. Okay, so that we considered as fa. Now here important recall. The recall is basically image of a set under a map f a to b. So let f is a function from a to b and s is a subset of a. So here f is a function from a to b and s is a subset of a. Then the image of s is defined as so that may be the image of s. This is fs. So fs equals to all those fx such that x belongs to s. So this is basically image of a set under a map f a to b. Now we'll come to the problem. The problem is asked in Calcutta University Honors Examination, the B.Sc course. The question, it is given in the year of 2004. What is the question? Let f is a mapping from a to b be a mapping and p and q be non-empty subset of a. And p comma q be any two non-empty subsets of a. And show that f of p union q, this is equals to fp union fq. Okay, so how to solve this kind of problem? So what is given? Given if a to b is mapping and pq are non-empty subset of a. So it is given that f is a mapping from a to b. This is a mapping. So this is your a and that set is your b, and f is a map from a to b, where p is a subset of a. This is p, and say q is another subset of A. So this you can consider as Q. This is your Q. So it is also given P is subset of Q. Sorry, P is subset of A, and Q is also subset of A. So what we have to show here, we have to show that F of P union Q, that means image of P union Q, that will be union of image of P and image of Q. Now the question is how to prove this kind of problem, how to solve it. So okay, we will use the concept of, say, S equals to T, in which we will show S equals to T, we will show S subset of T, and then we will show T subset of S. From 1 and 2 we can show that we must say S equals to T. So we will break it into 2 steps. So we have first step 1, we shall show that F of P union Q, this is just you consider as S. So here S is image of P union Q and T is your image of P union image of Q. So that is subset of FP union FQ. This is our step 1. We have to show this part first. Then we will show the reverse part. That means FP union FQ is subset of F of union Q. So what we will take, let say some Y belongs to F of P union Q. Okay, so that we can consider, okay, that this is the set F of P union Q. And we have taken an element, say Y here. Now see, Y is basically image of P union Q. So then by definition, there exists an X belongs to P union Q such that F of X equals to Y. Okay. So since here X belongs to P union Q, what exactly mean by this? That implies X belongs to T or X belongs to Q. So now in that case, the first case 1, if we consider if X belongs to P, then we can say Fx belongs to F of P. And that implies Fx means Y belongs to F of P. That implies Y belongs to, in that case, FP union FQ. Why? Because since F of P is subset of FP union FQ. Again, case 2, if X belongs to Q, then we can show Fx belongs to F of Q. And Fx means Y. So Y belongs to F of Q. That implies Y belongs to F of P union F of Q. Again, image of Q, this is also subset of FQ union FP. If we combining case 1 and case 2, what we say here? So therefore, by case 1 and case 2, what we conclude? We conclude that in the both cases, Y belongs to FP union FQ. So here Y we consider as belongs to image of P and Q, that means F of P union Q, and that implies Y. So therefore, we proved here Y belongs to F of P union Q. that implies Y belongs to FP union FQ. From that we can write F of P union Q subset of FP union FQ. Why? Because since Y belongs to F of P union Q, this is basically arbitrary element. Now what we will prove? What should be the step 2? Now we will continue step 2. So here we shall show that F of P union F of Q, this is subset of F of P union Q. That we have to show. So okay, we will take an element from F of P union F of Q, and from that we will show if that particular element belongs to F of P union Q. So let again we take say B. Let B belongs to F of P union F of Q. And at last we will show then what we can say, B belongs to F of P or B belongs to F of Q. Now case 1 again, if B belongs to F of P, then there exists an element A belongs to P such that F of A, this will be B. And case 2, if B belongs to F of Q, B belongs to F of Q, then there exists element A belongs to Q such that F of A equals to B. So in the both cases we must have, we must have B equals to FA for some A belongs to P union Q. That A may be either in P or in Q. Okay. So that means here, therefore, for some A belongs to P and Q, since A belongs to P union Q, that implies FA belongs to F of P union Q. FA means B. So B belongs to F of P union Q. So what we have shown here, therefore B belongs to F of P union F of Q, that implies B belongs to F of P union Q. Since B is arbitrary, so therefore F of P union F of Q, this will be subset of F of P union Q. Since B belongs to FP union FQ, that is arbitrary. So therefore or thus, from step 1 and step 2, we conclude that F of P union Q equals to FP union FQ. Now I will come to the next problem. This is problem number 11. Now we will come to problem number 12. So this question is asked in the year of 97 and as well as 2004. State true or false with justification. If f x to y is the mapping and a and b are subset of x, then f of a intersection b, this will be f a intersection f b. For 2 marks problem. And you can easily verify that this statement is false. For union it is true, but for intersection it is false. So here is the solution. The given statement is false. Now why it is false, that we need to justify. So we need justification. Otherwise we can't say it is false. It is false. So we have to set up some example, and through this example we can prove this is false. So let say the set is A equals to 1, 2 and B equals to 0, singleton set 0. Okay, say here we consider say when B and we consider the map f of 1, this is equals to f of 2 equals to 0. So we have considered the map. Okay, so this is your x, sorry. This set is your y. Okay, so here this is x, this is y at 1, 2, 0. Okay, so then obviously f is a mapping from x to y is the mapping. Okay, so now we consider the set P and Q. So let here A equals to singleton set 1 and B equals to singleton set 2. So this is your x and this is your y, and 2 under the map F, this is basically 0. So here this set is your A and you just consider the set is your B. Okay, and then so f of A equals to f of B and both are basically singleton set 0. Okay, so f of A intersection f of B, this is basically because both contains the element 0, again it will be a singleton set 0. But if we think about P intersection Q, sorry, A intersection B, so A intersection B, so A is 1, intersection 2, so this is basically 5. That implies f of A intersection B, this is also f of 5 and this is 5. So it is not the singleton set 0. That means it is not FA intersection FB. So what we proved here, f of A intersection B, this is not equals to FA intersection FB. So for intersection, this result is basically image of intersection not equals to the intersection of individual image. But when this condition will be true, that is our next question. And this question also asked in different examination, and it is also asked in Calcutta University previous year problem. So now we come to this problem, and this problem will be our question number 12, 13. This question asked in Calcutta University in the year of 1999. And also this question is asked in another year. Okay. So what is the question? The question is, let if A to B is an injective map. This is very, very important. Previously it was just a mapping. Now it is given, it is an injective mapping. Okay, from a set A into the set B, if C and D are subset of A, then prove that f of C intersection D, this is equals to FC intersection FD. Now the question is, initially for intersection, the image of intersection not equals to the intersection of individual image, but it is true if F is injective mapping. If you have asked the question when, for the previous question, when the intersection will be true. So that means when A intersection B equals to F of A intersection F of B, where AB are subset of X and F is a map from X to Y, when this result will be valid. The simple answer is if F X to Y is an injective mapping. Then the intersection is true. Other intersection of image equals to image of the intersection, that result will be true, otherwise it will be false. That we have already set up the counter example. But now if F is injective map, so here F is a map from A to B, that map is F, and C and D, so this map is C and this map is D. Okay, and this is basically the intersection part of C intersection D. And if we consider this will be your FC and this will be your F of D, so that part, this part will be FC intersection FD. Okay, and that will be valid because of the injectiveness of the map. So now we'll come to the proof, or you can say the solution. How to prove it? So first we'll prove, think about two steps. Step 1, we shall show that F of C intersection D is subset of FC intersection FD. This will be our first part. And step 2 will show F of C intersection D superset of FC intersection FD. And from these two steps we can conclude F of C intersection D equals to FC intersection FD. I will prove. So take any y belongs to f of c intersection d, then by definition of the image, there exists x belongs to c intersection d such that f of x equals to y. Now since x belongs to c intersection d, x belongs to c intersection d, so that means x belongs to c and x belongs to d. That implies fx belongs to f of c. Here is also fx belongs to f of d. So fx means y. Okay. So that implies y belongs to fc and y belongs to fd. Master. From the definition of intersection, what we can say, y belongs to fc intersection fd. So therefore, y belongs to f of c intersection d. That implies y belongs to fc intersection fd. And since y is arbitrary, so what we conclude, f of c intersection d subset of fc intersection fd. Since y belongs to f of c intersection d, this is arbitrary. Now we'll come to step 2. Step 2. We shall show that f of c intersection f of d, this is subset of f of c intersection d. How to show or how to prove this kind of problem? So let us choose V belongs to FC intersection FD. So in that case we can write then V belongs to FC and intersection means and by the definition of intersection, and V belongs to FD. So B belongs to FC, that means there exists x1 belongs to C such that say A1 belongs to D such that f of A1 equals to B, and V belongs to FD, that means there exists x2 belongs to D such that A2 f of A2 equals to B. Okay, so thus what we get, f of A1 equals to f of A2, that is equals to B. Now, since f of injective, so f of A1 equals to f of A2, that must imply A1 equals to A2, because if A2B is injective and A1 comma A2 both belongs to A as C comma D subset of A. So what we conclude? We conclude was just we take A1 equals to A2, take A1 equals to A2 equals to A, say. So that means f of A equals to B, where A equals to A1 belongs to C, so A belongs to C, and as well as A belongs to D. And that implies f equals to B, where A belongs to C intersection D. So what we conclude here, since A belongs to C intersection D, that implies if A belongs to F of C intersection D, if A means B, that belongs to F of C intersection D, since if A equals to B. So therefore what we get? B belongs to FC intersection FD. That exactly implies B belongs to F of C intersection D. That means F of C intersection F of D, subset of F of C intersection D, since B belongs to FC intersection FD, this is arbitrary. So thus, from step 1 and step 2, what we conclude? We conclude that F of C intersection D, this is equals to FC intersection FD, where if A to B, this map is injective mapping. So we prove this result. So our proof is done. Now we'll think about another important definition. So the definition is pre-image of a set. Pre-image of a set under some mapping. So let F is a mapping from A to B and S is subset of B. So this is your A, this is your B, and F is a mapping and S is subset of B. So then pre-image of S under F is defined as F inverse of S. Okay, and this will be all those A belongs to A such that FA that exactly belongs to S, such that FA belongs to S. And it is important to note that F inverse is obviously subset of A. Next question, this will be question number 14. And this question asked in the year of 2008. What was the question paper? Let capital is be a finite set and F is a map from S to S. If F is 1-to-1 map, that means injective map, then show that F is onto. In fact, we can show that F is bijective. There is another part of this question paper. Examine whether this remains true, this remains true if the set S is infinite. If the set S is infinite. So in the second case, we will see this result is not valid. It is valid only if S is finite set and if S to S be a map. So that means F is an injective map from the set finite set to itself, same set. So this is your S and this is your S again. Number of element in S say n and this is finite. And obviously the cardinality of the set is also finite. And F is a map. That map is injective. So 1 to 1 this is given. What we show? We show that F is onto. So here the solution, first part. First part, what is given? It is given that S is a finite set. This is given. And also it is given F is a function from S to S. And it is given F is injective. This three condition is given. What we have to show that? We have to show that F is onto. That means surjective. So how will show F is surjective? So if we show S equals to Fs, surjective means A to B surjective Fa equals to B. So that is we have to show that F of S equals to S, where F is basically mapping from S to S. So this is our target. Okay. So by the definition of map, we say that if S to Fs, this is surjective. This is onto. If S to S may not be 1 2, that we don't know, but okay, we can say if S to Fs is 1 2, that we can easily say. So since F is injective and if S to Fs is surjective, so what we include? F is a bijection, F is bijective from S to Fs. From S to Fs. Okay, so this is your set S, this is also S. That set you can consider the image of S, Fs. So F is injective and we can easily say if S to Fs is surjective. So that means if it bijective from S to Fs. I am not saying if S to S, if S to Fs, the image set. And since F is bijective, so therefore the cardinality of the set is equals to cardinality of the image set Fs. Okay, so that means we are recall this if is a map X to Y, this map is bijective. So then the cardinality of X must be the cardinality of Y. Okay, so here S to Fs is bijective map. So that's why the cardinality of S equals to cardinality of Fs. Since Fs is always subset of image set, always subset of S. Okay, so here our map is S to S, and that you can consider as the image set. We know the range of F or image of F always subset of the codomain. Okay, so here image of F is basically Fs, codomain is S. So Fs must be subset of S. So what we can say, cardinality of S minus Fs, that set cardinality. That will be cardinality of S minus cardinality of Fs. Here we have seen that the cardinality of S and cardinality of Fs are same. So that means it will be 0. Since why it is 0? Since S is finite. Okay, finite set. So cardinality of S must be finite. Difference of two finite number but same number, say 2 minus 2 or 3 minus 3, the value will be 0. But we can't say infinity minus infinity equals to 0. This result is not valid. But okay, n minus n, that will be 0 where n is finite number. So cardinality of S is n, say if its cardinality is n, say n minus n, it is 0 because this is finite set. But this not holds for the infinite set. So thus, what we can say, F is a subset of S and cardinality of the set S minus F is 0. So that means S equals to Fs. Okay, that we proved here. And since S equals to Fs, so hence Fs to S is onto. So what we proved? We proved if S is finite, so therefore if S is finite and if S to S is injective, then if S to S is surjective. But the next question is examine whether this remains true if S is infinite. No. This will be invalid if S is infinite. This is not true. But okay, we will show the counter example why it is not true. So that will be the second part. So the above result is not true if S is an infinite set. In general, it is not true. So we need a counter example, suitable counter example, and through which we can show if S to S is injective, that does not imply F is surjective. So let you will consider S equals to N and define a map F n to n as follows. N means set of natural number 1, 2, 3, 4 and so on by f of n equals to 2n for all n belongs to natural number. Then easily you can verify f of n1 equals to f of n2. That implies n1 equals to n2 for all n1, n2 belongs to n. And that implies if n to n, that map is injective map. Okay, just you try to visualize this map n, and here is also n. Here 1, 2, 3, 4 and 5, 6. 1, 2, 3, 4, 5, 6 and so on. So 1 goes to 2, 2 goes to 4, 3 goes to 6. So what we have seen, the element 1 in the codomain set or 3 or 5 in the codomain set has no preimage. So this map is injective but not surjective. Why? But if is not surjective, or you can say 1, 2. Why? Since if we take 1 belongs to n or 3 or 5, any odd number belongs to any odd natural number, or n is codomain, that element, you will take this element. So this element has no preimage. Then 1 has no preimage in the domain set n. under the map F, under F. So that's it is not surjective. Okay. So when S is infinite set, you will see this is an infinite set. Okay. So clearly S is an infinite set because it contains infinite number of elements. So if it is infinite set, then result may not be valid. The injective map may not be surjective. But okay, if it is finite set, then from the finite set to itself, it obviously injective implies surjective and surjective also implies injective. Now we'll come to next important question. This is about composition. And I said previously the definition of composition map. Say composition map, the definition is F is a map from A to B and G is a map from C to D and range of F is subset of dome G if then G composed F from A to D is defined, well defined, and G composed F is defined as this is equals to G of Fx for all x belongs to A. Okay. And here the question, this is question number 15 and this question asked in the year of 2003. What was the question? State true or false with justification, What was the question? Let F is a function from Z to Z and G is also function from Z to Z are given by F of x equals to x plus 1 and G of x equals to 2x plus 3. Then G composed F is a surjective map. Is a surjective map. Surjective mapping. So this question is basically for 2 marks question. So first we will find out G composed F, then we will check it is false or true. We'll come to the solution. We don't know it is false or true, but okay, we'll justify. So what is exactly given as a function F? So F Z to Z is defined by F of x equals to x plus 1 for all x belongs to Z and G is a function from Z to Z is this is also defined by G of x equals to 2x plus 3 for all x belongs to Z. So this is Z, F is a map from Z to Z, G is a map from again Z to Z, so that will be G composed F. And this map also Z to Z. So therefore G composed F Z to Z is G composed F of x. So here it will be x, that will be fx, and this will be G of fx. That will be G composed F of x. So this will be according to the definition of composition of map G of fx. So G fx means x plus 1. G is 2 into x plus 3. So 2 into x plus 1 plus 3. It will be 2x plus 5. So that means therefore G composed F Z to Z is defined by G composed F x equals to 2x plus 5 for all x belongs to Z. And you will see this number is always odd number. Okay. So which is now the image here, you will take Z, and this is also Z, 1 0 1 2 3 4, minus 1 minus 2 minus 3 and so on, 0 1 2 3 4 5, minus 1 minus 2 minus 3 and so on. So 0 goes to 5. Okay. So since 2x plus 5 is an odd integer for all x belongs to Z. So if we take, so x goes to 2x plus 5. If we take any even integer in the codomain set Z, then it has no preimage in the domain set Z. As for example, if we take, or in particular if we take 0, that element in the codomain set, 0 belongs to Z codomain, then 0 has no preimage in the domain set. Why? Because as 0 is not an odd integer. Okay. So therefore, here G composed F from Z to Z is not surjective. Okay, thank you so much. Next class we will solve the problem from question number 16 to question number 20. So in each class we will solve at least 5 problems. Thank you so much.